My name is Charlie Yang. I'm going to present our paper analyzing the interplay between random shuffling and the storage devices for efficient machine learning. This is a joint work between NTU and Academia Sinica in Taiwan. Mini-batch gradient descent is commonly used for machine learning training, like a support vector machine and deep neural network. In each iteration, the ML model is trained with a batch of training instances. Training the entire dataset once is called an epoch. The process is repeated until the model reaches the convergence condition. For mini-batch-based machine learning, the way to organize batches greatly impacts training efficiency. Random shuffling is a process to ensure training data instances are fed into the model in different orders in each training iteration and epoch. This can improve both testing accuracy and the convergence rate by avoiding overfitting and preventing the training process from getting stuck in the local minimum. If the underlying storage system is disk, an efficient random shuffling implementation needs to avoid frequent random disk accesses. This often leads to less random degree. Next, I will describe two commonly used random shuffling implementations for support vector machine and deep neural network. For SVM, we adopt the BMF implementation, block minimization framework. In BMF, there is a preprocessing process, which reads the training data from the disk to the memory sequentially and write back training data to randomly selected files. During the training phase, BMF only shuffles the batch order between epochs. This implementation minimizes random disk accesses, but it requires a long initial shuffling process and a compromised random degree. For DNN, we adopt the Tensorflow Input Pipeline Implementation, TFIP. Similar to BMF, TFIP also requires a preprocessing phase, which reads the training data from the disk to the memory sequentially and then write back to disk in random order. In the training phase, TFIP loads partial training data sequentially into the random shuffle queue in the host memory and only randomly shuffle the training data in the queue. TFIP avoids frequent random disk access, but it requires a long initial shuffling process, and the random degree is limited by the size of random shuffle queue. The figure shown in this slide shows the testing accuracy of two NN models under different queue size. We can see that a larger queue size can offer higher testing accuracy. One of the workloads studied in this work actually requires 80 gigabytes for the random shuffle queue in order to achieve good accuracy. Solid-state drives have been widely adopted, not just in the embedded devices, but also in the high-performance computing platforms. SSDs offer much higher random access throughput than disk. In this table, we list two Intel SSD models. One is flash memory, and the other is in Optane memory. We can see that both SSDs offer much higher random access IOPs than disk. The flash SSD is 716 times faster, and the Optane is 916 times faster. So the problem we study in this paper is that can we design a more efficient random shuffling implementation than BMF or TFIP by exploiting the fast random access property of SSD? In this work, we design a lightweight implementation of random shuffling called LIRS, targeting at SSDs. In LIRS, the host maintains a random assignment table, which records the instance ID randomly assigned to each batch, and this assignment table is updated at each epoch. When we start training a model, LIRS looks up the random assignment table and then brings the training instance to the host memory based on the information stored in this table. In this example, the first batch contains training instance 1, 5, and 8. So these three instances are brought into the memory through random reads. A naive implementation of LIRS has some inefficiency due to the paging system, which brings data from the storage to the memory in the granularity of pages. In this example, the first batch contains instance 1 and 4. When we load the first batch into the memory, we bring in 2 pages. If other training instances in these 2 pages are used after these pages are evicted, then it causes wasted I/O transfers. The second source of inefficiency comes from page alignment. In this example, training instance 7 crosses page boundary, so we need 2 reads to bring in batch 1. If page k plus 1 is evicted before instance 6 is used, then this results in redundant page transfers. To solve this inefficiency, we propose 2 methods. The page-aware shuffling mechanism assigns training instances in the same page to a batch. This could greatly reduce I/O transfer time, but it limits the random degree. The second optimization is called padding, which requires an initial process to scan through the entire training dataset and add zeros at the end of page to realign instances when needed. Compared with the BMF and TFIP approaches, LIRS does not need the initial full-range shuffling process, and since it has higher random degree, the training process could converge faster and could even potentially achieve higher testing accuracy. For DNN training, LIRS does not need to reserve a large memory space for random shuffle queue as TFIP. We evaluated different random shuffling methods on disk, flash SSD, and Optane SSD. The experiments were conducted on a computing platform with Intel i7 processor and NVIDIA GTX GPU. For SVM, we evaluated 3 datasets. For DNN, we evaluated 5 different models. The overall training time is defined as the time to converge to a predetermined accuracy requirement. The first set of experiments are for SVM BMF implementations. The training time is decomposed into the pre-processing time, computation time, and loading time. If we simply replace hard disk with a flash SSD, the loading time could be reduced by 26.8% on average, and Optane could reduce the loading time further. But for the overall training time, the performance improvement is roughly 10%, even using the latest Optane SSD. With LIRS implementation, using SSD could achieve up to 51% total training time reduction. This mainly comes from shortening the computation time. This chart in the slide shows LIRS take fewer numbers of epochs to reach the converge condition. Our results show that BMF needs 30 epochs for the 3 test sets, while LIRS only requires 10, 5, and 3 epochs, respectively. Using Intel Optane could further reduce the loading time compared to flash SSD. For SVM, page-aware shuffling appears to be quite critical for the first 2 datasets, since they have very small training instances. The third dataset, splice site, has training instances larger than the page size, so we do not apply page-aware shuffling. Padding could further reduce the loading time. In the aspect of testing accuracy, LIRS does not show advantage compared with BMF. That is because the objective function of linear is less likely to stuck in a local minimum, even if the instances are not thoroughly shuffled. The next set of experimental results are for DNN. In the TFIP implementations, The loading time could be overlapped with computation, so adopting SSD does not have a significant performance gain. But with LIRS, we see 33.5% total training time reduction with flash SSD. This gain mainly comes from computation time reduction. Over the 5 models we tested, LIRS have smaller validation loss than TFIP, so it takes fewer efforts to converge, roughly between 70 to 80% of TFIP. With Optane, the loading time could be further reduced by 8.2%. For DNN, page-aware and padding optimization causes negative effect on training time. Recall that page-related optimization could reduce loading time at the expense of lower random degree. Since in the TFIP implementation, the loading time could be hidden with computation time, the negative effect of lower random shuffling degree outweigh the gain. In the aspect of testing accuracy, LIRS achieves up to 1.9% accuracy improvement compared to TFIP. In this paper, we study the interplay between different shuffling methods and different types of storage devices. We develop LIRS as an example of SSD-aware random shuffling methods. LIRS can achieve full range random shuffling without taking up precious CPU memory. Finally, we showed that simply replacing hard disk with SSD can't fully exploit the performance advantage of SSDs. A full-range shuffling method, such as LIRS, is necessary and beneficial.